Hello everyone, welcome back. I, Pratyasha, on behalf of IEEE PES Student Branch Chapter, IIT Kanpur, welcome you all to the evening session of the ongoing online technical workshop PERA 22. PERA 22 is the third edition of our flagship event, Power Engineering Research and Applications, organized by IEEE PES Student Branch Chapter, IIT Kanpur. This year's theme, Towards Sustainable and Resilient Power System, aims to uncover the state-of-the-art of several present-day and future opportunities and challenges related to the sustainability and grid resiliency. I hope that this event will provide a platform for students, young professionals, researchers, faculties, and practicing engineers to explore new and exciting ideas in the field of resiliency. I would now like to welcome all the audience and our first speaker for the evening, Professor Francisco M. Gonzalez-Longatt. Professor Francisco M. Gonzalez-Longatt is currently a professor in electrical energy systems at the Center for Smart Grid at the University of Exeter and is invited full professor in electrical power engineering at Universitetet for Electro Norway, also the founder and leader of the Digital Energy Systems Laboratory and a global research initiative for digital energy systems. His academic qualifications include first-class electrical engineering from Instituto Universitario Politécnico de la Fuerza Armada Nas- Nas-
Nacional.
National Venezuela 1994, Masters of Business Administration, honors from Universidad
Bicentenario.
Bicentenario de Aragao, Venezuela 1999, PhD in Electrical Power Engineering from the Universidad Central de Venezuela 2008, and postgraduate certificate in higher education professional practice from Coventry University 2013, and diploma in leadership and management ILM level 3 Loughborough University 2018. He is the author or editor of several books, Spanish and English, including Power Factory Applications for Power System Analysis, Springer, Advanced Smart Grid Functionalities based on Power Factory Springer, and Dynamic Vulnerability Assessment and Intelligent Control for Sustainable Power Systems, WILLY. He has written 20 plus book chapters, 50 plus journals and magazine papers, and 100 plus conference papers. His work is over 4.5K citations, and his H index is 28 as per November 2021, according to Google Scholar. He has been invited professor at the Master on Renewables at University of um, Seville, Spain, Master of Renewable at University Carlos III Madrid, Spain, and many other universities worldwide. He has been invited speaker at several top universities, keynote speaker at several important conferences. He is an associate editor in several top-ranked scientific journals in the area of power system. He is vice president in Venezuelan Wind Energy Association, senior member of the Institute of Electrical and Electronic Engineering, a member of the Institution of Engineering and Technology UK, the member of International Council of Large Electric Systems. He received professional recognition as Fellow of the Higher Education Academy in January 2014. His research interest includes innovative operation and control schemes to optimize the performance of the future energy systems. His research is or has been supported by Royal Society, British Council, UK India Education Research Initiative. He has been collaborating in European research projects also. Two special projects financially supported by the Royal Society and British Council deserve mention: Exploring Beyond the Frontiers to Build a Smarter Grid and and Smart Multi-Terminal DC Microgrids for Autonomous Zero Net Energy Buildings. May I, May I now kindly request Professor Francisco M. Gonzalez-Longatt to convey his rich knowledge in this field by delivering his expert lecture on experiences using real-time simulation to ensure secure future power systems. Sir, please.
Thank you so much. Let me start to share my screen, please. And
recording in progress.
Sir, I hope we have your consent to record this session.
Yes, please. It's not a problem. I will be recording also by myself. Thank you.
Okay, sir. Thank you.
Well, very good afternoon, very good morning, very good evening, depending on if you are located. I can see that there are people from several places around the world. And I would like to start this presentation saying thank you very much to the organizers and the IEEE and the IEEE PES student branch from Kanpur. It's my pleasure being here and sharing some of my expertise and knowledge about real-time simulation. The presentation will be relative short in terms of what I can present in 45 to 60 minutes. And the topic today is experiences using real-time simulation and focusing basically on the future power systems. Before I start, let me tell you that I am recording this presentation and also will be uploaded to my YouTube channel. Also, there are many of my presentations located over there. I have a lot of entries in Google, and my career has been quite interesting between different countries. I started in Venezuela, in South America. Then I moved to the UK. I stayed for several years in the UK, basically the University of Manchester, Coventry, Loughborough. Then I moved for 3 years at the University of Southeastern Norway. And for me, the previous 3 years has been very, very successful because that was the starting point of the DHENSYS lab. In a minute, I will tell you more about DHENSYS lab, but it's basically Digital Energy System Laboratory. And the experience that I will share with all of you are coming from there. And finally, June 2022, I started my career again in the UK, basically at the University of Exeter. The University of Exeter, the most recent acquisition, I belong to the Center for the Center for Smart Grid. And when I say that the experience that I will show today are related with the DHENSYS lab, is because in 2019, when I arrived to Norway, I decided to start a small laboratory regarding real-time simulation. Real-time simulation, in a minute, you will get a formal concept, but it's a tendency for testing and developing new concept for energy system, especially when we are working with low carbon technologies and reducing rotational inertia. I started DHENSYS lab at the University of Southeastern Norway. Now it's becoming more and more important with more members worldwide. And there is a reason that I start to call that the Global Research Initiative. However, that is beyond the scope of this presentation. What you need to know is that basically DHENSYS lab, we have been doing research for the past 3 years, using basically 2 different brands of real-time simulator. Typhoon Hill, that you must be aware about that. However, in a minute, I will give you more information. And then also Opal RT, another of the technologies that is quite relevant for real-time simulation. Probably you are wondering, okay, why DHENSYS lab? Because I am a strong believer that the digital technologies can be used to improve the security and the resilience of the power system operation, the energy system operation. When we are talking about energy system, there are several challenges around the world. In many countries, you will find that some of them, they have issues related with frequency control, system restoration, system stability, voltage control, and thermal. And to be honest, all those situations coming from the integration of low carbon technologies, the solution is already near to us. What I can tell you is that in order to deliver secure and resilient electrical energy systems, what we need to do is take the advantages of several technologies. We can take advantage of the decarbonization. We are having more electric vehicles. We are having energy storage, and that energy storage is located near to the customer. For that reason, decentralization is a key point of solving the issues. And democratization, giving access to everyone to the market and to the energy system. And finally, for me, one of the key enablers of the future is the digital technologies. Digital technologies is a very interesting term because digital technology involves several things. Involve, of course, data science. You can know right now that we care about artificial intelligence, machine learning, deep learning, blah 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 blah. This is one area from digital technologies, but also extremely important for digital technology is the hardware. The hardware is also the computational power is one of the key technologies enabled for the secure and resilient future energy system. And of course, the communication. We are living in a digital area, and communication is one of the key points. For that reason, today my presentation will be basically showing some of the digital technologies using real-time simulation in order to increase the security and the resilience of the electrical power system. Well, this is the end of the introduction, and now I need to show you the agenda for today. The agenda is very simple. To be honest, here is very short. We will start with some general concepts. I usually like to go very slow at the very beginning and show you some basic concepts that there are many people that they don't understand those concepts. Then I will go through the different type of simulation in electrical power system. Some of those simulations you already know that. And then I will go for digital simulations in electrical power system, initially offline, and then I will go to the beautiful real time. I will focus basically in hardware in the loop. That is one of the paradigms used for real-time simulation. Then I will present some cases, and finally we are closing this presentation. Okay? Let me start with the concept. Everyone in this classroom, everyone in this area know a system. System is basically a set or a group of different components interacting each other, and all of them, they have a set of rules that will unify the performance. For instance, in electrical power system, we can imagine this like a small power system. We have generator, we have an infinite bus bar, we have a transmission line. However, if we look more into detail, we can see that the generation unit is having several subcomponents. We have a thermodynamic system, if we consider this a steam turbine. We have a mechanical system that is basically the steam turbine. Then we have electrical system starting from the generator, from the starter of the generator, going to the infinity bus bar. All those components, they have different environment and different physics behind that. And that is a starting point of the complexity in the electrical power system. On the other hand, the reality is that the systems, they are very, very complex because the power systems, especially the power systems, are basically dynamic systems. A dynamic system is coming from the original Newtonian mechanics. However, the concept is applied for electrical power system because in reality, the electrical power system is a system where the state variables are evolving over the time. And these changes on the state variable are basically following several of the possible changes coming from the input variable, but also for some possible strange or difficult signals like some disturbances, okay? However, the electrical power systems are complex. They have different physical nature. I say to you thermodynamical, mechanical, electrical, and so on. However, the core is for electrical power system, try to create models that replicate all that physics. And that is where the problem starts to be very interesting. Because in reality, we have the electrical power system with all the physics, but then we try to create a mathematical abstraction. The mathematical abstraction is coming from the model and the equations. And then when we have this model and the equations, what we try to do is basically solving those equations in order to get the system response. To be honest, this is a process that looks very simple. However, there are two very important parts during the modeling stage. One is the hypothesis that we are following, and then the simplifications. Because every single model has some simplifications in order to work. For instance, depending of the detail, the level of detail that you are interested, you can model an inductor like the classical voltage and current relationship. That means voltage equal a constant di dt. However, if you want to get the full detail of the performance of one inductor, well, probably you need to go to the Maxwell equation. What I'm trying to tell you is that the level of detail that you want to do in your model define the size and the complexity, the size and the number of parameters and the complexity of those models. And the reality is that also the size and the shape of those equations depend on the model. The computational model, we try to create equations. Of course, those equations can be algebraic or they can be differential. Typically for dynamic system, we use differential equations, and then we try to solve those equations. However, in this case, something that is very important during the task of modeling is that many models require validation and also parameter setup. Because in reality, we can have a very good mathematical description, but then that model must be adapted in order to follow the reality. That is the reason that one very important stage during the modeling is starting from an uncalibrated model that is not able to follow the data until we use some mathematical techniques and calibrate the model in order to follow the real data. However, even the most detailed and the most powerful models, always they have some possibility of miscalculating or misrepresenting the reality. Here in this slide, you can see something quite interesting. Here we have the forecasting, the 24-hour forecasting of the load demand in the Spanish system. And what is interesting here is if you look a very small time period, you can see a very small deviation from the real demand from the forecasting demand. Many people will say probably this is a very small error, but if you look the real numbers, we are talking about an error that can be 534 megawatts. That is huge in terms of power plant production. What I can tell you is that basically the models, they have some uncertainties when they are working with the parameters, but also with forecasting. And the sources of those uncertainties can come from many places. For instance, from the load. The customer behavior is something that is very difficult to forecast, even using the most modern artificial intelligence techniques. Also, generation. In generation, right now, we are installing a lot of renewables, and forecasting the PV or the wind speed is relatively easy. But if we consider the clouds that they are obstructing the sunlight, that is a more difficult system. Then we have uncertainty coming from the controllers, from the parameters, from possible faults, communications, but also some uncertainties coming from topology, electrical parameters from the grids, and so on. However, to be honest, those uncertainties, they are very simple and it can be managed. And they are in real life some uncertainties that they are extremely difficult to forecast. For instance, in real life, we have several events that they are very difficult to forecast. A volcano eruption, and earthquakes, landslides, hurricanes, explosion, accidental human actions, is very difficult to forecast. And that is the reason that today we are considering more seriously the concept of reliability. Reliability is now considering uncertainties and also events that they have extremely low probability. The reliability is a very interesting concept. The reliability is the probability that the electrical power system can perform the functions under given condition for a time interval. There are many standards defining that, and the reliability is basically divided into sub-areas. One that is related with the balance between generation and demand, considering scheduled and unscheduled outages. That is adequacy. However, the most interesting one for me in electrical power system dynamic is security, because security is related with sudden disturbances. And to be honest, those events that I was talking about, like explosion, eruptions, and so on, they are very, very related with very low probability, but with a huge impact. And that is the reason that security starts to be interesting. In recent time, in the electrical power system community, we have started to be very, very interested in a concept that is called resiliency. And resiliency is a concept that is not new. To be honest, power system engineers, we took the concept coming from the psychology, and you can see over there, what is resilience? The process of adapting well in the face of adversity, trauma, tragedy, blah, 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 blah. What I can tell you is that the concept was originally created by the American Psychological Association. And years later, to be honest, relative new, probably 2016, 2018, we established the concept of resiliency inside the electrical power system. And here I am presenting one very interesting document coming from the IEEE working group, the task force related with the definition and quantification of resilience. And as you can read here on the left-hand side, the resiliency is the ability to withstand or reduce the magnitude or duration of disruptive events, okay? This is something that we need to identify. Disruptive event is not a normal event. It's an event that is huge, catastrophic, or able to produce very, very bad conditions for the electrical system. But continuing with the concept, you can see that include the capability of anticipate, absorb, adapt, and rapidly recover from such event. That is basically the formal definition established by the task force in resilience, okay? The resilience is typically related to those disruptive events. In reality, you can imagine that this is the status. In the vertical axis, you can see the status of the system. In normal condition, what we call pre-disaster, the resilience, the status of the system is normal condition. But if suddenly we have a catastrophic event like an earthquake, flooding, hurricane, typhoon, or whatever, well, the status of the electrical system can be disrupted and affected. And as a consequence, the system can experience, for instance, blackouts or a reduction in the performance indicators and so on. That is what we call the disaster stage. The system has, of course, several controls, but also there are many engineers working in the system. For that reason, there is a possibility of restoration stage. That is the moment that the recovering forces in the electrical system try to reestablish the system status. And finally, there is a possibility of a long-term recovery process. The line that I just show here is what we call a less resilient system. And the reason that we call this less resilient system is because the status of the system is more affected during the disaster stage. And also during the restoration process is taking so much time. You can see here in this purple line that you can see during the disaster moment, the state of the system is reduced, but is recovered pretty fast in order to go near to the pre-disaster condition. Okay, this has been the representation of the resilient. We know the concept of resilient. What is the main difference between resilience and reliability? Well, I believe that everyone in this classroom, in this situation, knows the difference. Reliability is basically related with normal conditions. I mean, with events that they have a high probability. And to be honest, we have many situations in the electrical power system with high probability. For instance, the disconnection of generators, the sudden appearance of a short circuit, and so on. Those events, they are really bad for the system, but they don't create a disaster. In fact, this high probability make the power engineers to take some actions, and that is the reason that we have protection systems inside the electrical system. In order to cope with this kind of high probability events, minimizing the impact. But on the right-hand side here, wow, we have resilience. Resilience, they are events, they are created by events that they have very low probability. What is the probability of one earthquake? Typically, they are measured in number of time per decades or even centuries. But when an earthquake happens, of course, the impact of that event is huge. For that reason, we need to understand that resilience is connected with disasters. Is related with disasters and high impact disaster, okay? For that reason, the time for recovering from those disasters, it can be huge. Well, now it's time to connect the dots. Now we define resilience, we know the difference between reliability and resilience. Now, how do we calculate reliability and how do we ensure resilience? Well, electrical power systems, we have simulation tools. And the reality is that for many, many decades, the simulation tools has been in two very important sets. One set that is called the root median square simulations, or RMS simulation, and another set of simulations that they are called AMT, or electromagnetic transient simulation. What I'm trying to tell you is that the power system dynamics, the dynamic processes in electrical power systems, they can be divided in different time scales. They are very fast dynamics, they are very slow dynamics. And the AMT simulation, electromagnetic transient simulations, are dedicated for very fast transients, and the electromechanical processes related to the synchronous machine, they are typically studied by using root median square simulation. But let me show you in a minute the difference between them. The AMT simulations, they are extremely fast. For instance, we can study switching over voltages, short circuit currents in full detail, in rush currents. What is the main reason for that? Well, because we need to use the high order detail model of the electrical power system. We need to consider the dynamic of everything, including, for instance, the capacitance, resistance, and inductors located in the system, okay? Well, resistance, they don't have dynamics, the capacitors and the inductance. And because that, we need to use very small time step to solve the differential equation. Here you can see a very simple example. When we are studying AMT, we need to represent, for instance, the voltage-current relationship for the capacitor using the integral, and for the inductor using the differential equation. The good news is when we solve this, when we solve the AMT simulations, the solution will be instantaneous values representing the voltage currents, the electrical signals over the time. And then we have another set of simulations. The other set of simulation is what we call the electromechanical phenomenon or RMS simulation. In the RMS simulations, we do a very simple and a very interesting supposition. And we assume, remember that I say assumptions and hypotheses, we assume that the transients related with the transmission lines or the transmission system is very small, very fast, and we can use the assumption of the concept of phasor. I mean, when we are using RMS simulation, basically what we are doing is using phasors, assuming that the frequency is constant or almost the deviation of the frequency is almost zero. And from there, we can use phasors and we can use inductive and capacitive reactance in order to establish the relationship between voltage phasors and current phasors. Okay, perfect. Now, probably you are wondering why I am talking about this, because the RMS simulations is typically the tool that we use for power system dynamics. And basically what we do is consider the dynamic of the electrical machine, the electromechanical dynamic, and neglect all the electrical dynamics. And that is the reason that we have different type of simulation tools. We have simulation tools coming from many decades ago. Probably the first simulation tool that we have, it was the TNA. The TNA is also called an analog computer. To be honest, starting in 1929, we start to use the TNA. And what is the TNA? Well, you can imagine the TNA like a very small components. I mean, you have small transformers, you have small generators, small transmission lines, and you play like a Lego. What you are doing is interconnecting all those devices using low voltage and of course getting the measurements. What is the advantage of this? Well, this was the first computational tool that we use for simulations in electrical power system. It was simple and it was useful for steady-state performance. However, there are many phenomena that they cannot be scaled down, and as a consequence, the TNA start to be not so useful. The next step in the computational simulation of electrical power system analysis was the digital computer. The digital computer starting in 1940s, that was the starting point. We start to use those huge mainframes, using those punch cards for calculations, and then appear the large digital computers. Large digital computers starting in 1950. From there, the computer, the digital era start to be really important, and from there is the starting point of more powerful tools for power system analysis. And here is the very important point. You can see the horizontal line. The horizontal line is basically a timeline related with the evolution of power system simulation. I was talking about the analog simulation, then we tried to use analog digital, and then the digital computers. However, two very important moments in the real-time simulation, it was 1994, because RTDS Technologies, the Canadian company, was the pioneer of the real-time simulation. Originally, this company was a research project from Manitoba HVDC Research Center. And in 1980s, they started to develop the real-time simulation. And finally, in 1994, they established the first real-time simulation and the first device. Then, in 1997, again in Canada, I don't know why in Canada, but Opal RT Technology established start the journey in 1997. They start the simulation, digital real-time simulation, using the OP5600. That was the first technological development of Opal RT. And finally, my friends from Typhoon Hill, they start the journey in 2009. These are probably the three most important companies providing digital real-time simulators. In a minute, I will tell you what is a digital real-time simulator. However, what you need to understand is that is a very computational intensive and efficient computer. And we will discuss the concept in a minute, okay? Okay, let me move forward. What does mean digital real-time simulation? To understand the paradigm, I will start with the old generation of simulators. The old generator of simulators is what we call offline simulation. To be honest, a simulator is any tool that allows us to solve the model of the electrical system. And all of you must know that if we are interested on the power system dynamics, well, we use the differential algebraic model. And the differential algebraic model is a continuous problem. We solve the problem using a discretizing process where the time is discrete. And then from there, we use some algorithms, some methods to solve those equations. To be honest, what I'm trying to explain in a simple words is we start here from a continuous problem. We have one equation that is a differential equation. We have an algebraic equation. This is a continuous problem. From there, what we'll do is take the time and divide the time into small pieces. And then inside those small pieces, we are solving in a systematic way the set of differential and algebraic equations. And that is what we call the discretized problem. As you can see over here, the time have a subscript, and that subscript represents each one of those time steps. But now we have an issue because we have the real time, and that is the simulation clock, and we have the computational time. What does mean computational time? Computational time is the time that we require to solve these equations over here. And we can spend this time, spend this time, and spend this time. But when we are solving that, the real time is moving forward. What I can tell you is that when we are solving offline simulations, when we are solving off-time simulation, we have two possible scenarios. Well, there are three, but the third one is not happening quite fast. There are two important scenarios. Faster than real time and slower than real time. What does mean faster than real time? Well, if we are looking into the clock, you can see here a time step. And the solution of the differential equation, could you see that the solution is faster than the time that we are looking into the clock? But the worst case scenario, and the scenario that typically happens, is that the solution of the differential algebraic model require more time than the real time. What I'm telling you is if we start to solve second one and second two, and this is the computational time, and we are looking to your clock, you can see 1, 2, 3, 4. You can see that you get the result after we reach the second number 2. That is what we call the simulation of light simulation slower than real time. For that reason, what I will do now is I will show you a couple examples, because it's typical that people are confused about this. Let me start with this simulation. Over here, you can see the PM Anderson 9-bus system. The 9-bus system is a very well-known system, but I create a slightly modification. Here you can see the load profile. This is the load profile, and this is a 24-hour load profile. And if you want to see the full simulation, you can go to my YouTube channel, but I will show you here something quite interesting. I record this video and I will run the simulation using my favorite tool that is called the Excellent Power Factory. Wow, this was faster. As you can see, I am reducing the video speed. And right now, I am running this at very slow motion. And you can see to run 24 hours, I am taking 1.1 second. That means that a simulation that is supposed to replicate the behavior of 24 hours is taking 1.1 second. This simulation is faster than real time. But now, I'm sorry, I pressed the wrong button. But now let me do the following. Let me go to the next case. Now I am running a AMT simulation, and look over here. Right now we are running the AMT simulation that is heavily computational for this computer. And you can see something quite interesting. The clock on the top is the real clock, and the clock below is the simulation time. I don't know if you can see the discrepancy. Let me stop the simulation here. What you can see over here is that to simulate 12 seconds, we are spending 21 seconds on computational time. What I can tell you is that this simulation, of course, is slower than the real time. And now I believe all my students in this classroom start to understand the complexity, because the complexity of real time start to be apparent, because you can see that real time means that the simulation time and the real time, they must match. For many years, we have been using offline simulation. For many years, we didn't care about if the simulation time matched the real time. But in recent time, power systems start to be more complex. And the complexity of the power system is coming from many areas. It's coming from the diversity of the physical phenomenon. It's coming from the non-linearity of many of the power system dynamics. But also right now we are integrating many stuff that they are improving the performance of the electrical system, but at the same time is creating another source of problems. We are in the digital era. In the digital era, there are many software. There are many communication possibilities. There are also computational aspects. And all of them are creating a very interesting issue. Right now, we have some physical components that they have a strong influence on the dynamics, but also we have the communication, we have computation, we have many other devices and aspects that they are influencing the dynamics. And most of them are coming inside a computer, a piece of software that is affecting the dynamics, and that is the cybernetic layer. For that reason, in recent time, the motivation to go into the real-time simulation has been basically the need for integrating different phenomena. The physical layer, the synchronous machine, the transformer, the transmission lines, but at the same time, that cybernetical layer that is related with communication, with informatics, with computational power. And that is when we start to care about digital real-time simulation. We start to care about digital real-time simulation because right now the controllers, the actions that we need to take in the electrical power system, they must match the real clock that you have in your hand. That is the reason, the motivation behind having real-time simulation. The first thing that you need to know about real-time simulation is that 1 second in the CPU must be equal 1 second in your clock. And I don't know if you realize, but that is a huge technological problem. Because in the previous sections, I told you about offline simulation. Offline simulation, you can be faster or slower than real time. And to be honest, there is no problem. Because if you are faster or you are slower than real time, nothing will be hugely affected. But in complex system that you have the integration of many components like informatics and so on, digital real-time simulation, real-time start to be a very important thing, okay? Now, what is digital real-time simulation? Well, digital real-time simulation means that we will be able to produce voltages and currents that they match this real behavior of the electrical system. But I'm not talking about the instantaneous values. I am talking about the time. As I say before, in a digital real-time simulation, the time that you are using for computation should be equal to the time that you have in your clock. And to do so, we need a device, and that device receives the name real-time simulator. The real-time simulator has a software and has a hardware. But the hardware is the very important component, because inside the hardware we have a CPU and we have a FPGA. Yes, we have a CPU that is similar to the CPU that you have in your computer. But now we have a piece of hardware that is highly flexible and reconfigurable, and that is the FPGA. But now probably you are wondering, where is the challenge? Well, the challenge is, if you remember, we tried to solve the differential algebraic model. We tried to solve the differential algebraic model basically using the discretization of the time. That means that for every single time step, now we need to do something very important. We need to send data to the CPU. We need to solve the equations inside the CPU, and produce results. Well, what we realize is that using the CPU and the FPGA, we can accelerate a lot the computational power. The modern real-time simulators, they have a CPU that we use for solving problems with relative small time scale. For instance, microseconds. And then we have another problems that they need to be solved in a very fast fashion. And that is the reason for using this very highly flexible, reconfigurable software, and that is the FPGA. Here we are talking about nanoseconds time scale. Well, the real-time simulator is doing this inside. And that is one of the reasons that the hardware of the real-time simulator is a bit expensive, because we require a lot of technologies, okay? Well, finally, the question is how to do with the real-time simulator, what to do with the real-time simulators. Well, the real-time simulators, they can produce signals, voltages, and currents, small voltages and small currents, but we can use those signals for testing actual physical system. In a minute, I will show you some of the study cases, but you must understand that the physical system can be, for instance, a protection, a controller, and so on, okay? Well, we are running out of time, but I will show you two of the basic implementations that we have in the lab. In the DHENSYS lab, we have Typhoon Hill technology, we have Opal RT technology. And Typhoon Hill and Opal technologies are two of the most famous vendors for real-time simulators. Here I can show you the internal components of one of them. This is a Opal RT 4510. You can see here the multi-core. Here we are using a CPU. This is the CPU. It's a multi-core CPU. And here at the top, you can see the FPGA. But more important, we have inputs and output, analog and digital. And those inputs and outputs can be used to interface with many components. And now what I would like to do is to show you the paradigms that we can find using digital real-time simulation. Using real-time simulation, we can do what we call fully digital real-time simulation. That means in this paradigm, we can test models, we can test software, but where the real-time simulation take off and is brilliant is hardware in the loop. This is one paradigm. This is basically testing software or models in real time. But here is where the things start to be very interesting. Here we can use the real time connected to real devices, and we have power hardware in the loop, control hardware in the loop, and a paradigm that I have been using for 3 years, and that is relay in the loop. I can see few questions related with the, there are several questions appearing in the chat, and I will try to cover them here. Hardware in the loop is the paradigm that I love because it's where the real-time simulation shine. Because in the hardware in the loop, we are using the real-time simulator, but the real-time simulator have inputs and outputs, and they then can be connected, to a prototype. For instance, there are two approaches for the hardware in the loop. One that is low power. I mean, we have the real-time simulator, we have here the CPU and the FPGA. They have the inputs and outputs, analog to digital converter and digital to analog converter. And here we can send and receive control signals and receive feedback, but this is low power. In a classical controller hardware in the loop, we can use plus 5 volts or plus 15 or 24 volts depending on the manufacturer. However, my favorite is the power hardware in the loop, because in the power hardware in the loop, you have your real-time simulation here, you have the converters for sending signals and receiving signal, but you have here what we call the power amplifier. The power amplifier is receiving those small signals of 5 volts, and here we can send and receive signals to 130 volts, 3-phase, or 5 amps, 3-phase. That means that with power hardware in the loop, you can assess the real hardware. And for resiliency, this is extremely important. Because for resilience, you can create here the model of your test system. Then that test system can be compiled and sent to the real-time simulator. And here you can create a disaster event. In this disaster event, it can be a flooding, it can be a thunderstorm, whatever. And when we have this event, we can create signals, and those signals can go to a piece of hardware. For instance, we can use a relay, and the relay will receive those signals, and depending on those signals, the relay can create a response. And using the appropriate indicators, we can use this framework to test concepts related with resilience. Okay, I will show you some example here. This is controller hardware in the loop. This is a paper that we published a few years ago. It's basically we are trying to test a new frequency, primary frequency control with a battery energy storage. Here we have some hardware in the loop. We create here the model of the battery energy storage. We create the model of the control. And what we'll do is we put inside an Arduino, a low-cost single board computer, an Arduino Due. And here we send signals, analog signals, and receive analog signals. And in this way, we were able to assess the performance. Here you have the simulation. This is the offline simulation. And here we have the real-time simulation. I don't know if you can see, but there is a huge discrepancy. When you are doing offline simulations inside MATLAB and Simulink, look over here, those signals are perfect. You can see that this is smooth and so on. But when you are using digital real-time simulation to test your controllers, you can see here the noise. And that is one way that you can test the resilience of your controllers to survive different level of noise. Here I will show you some power hardware in the loop. In the lab, we have Typhoon Hill and we have signal conditioning or power amplifier from Typhoon Hill. For that reason, for testing power hardware in the loop, we have the real-time simulator. This is a Typhoon Hill 604. And from there, we interchange signal with the signal conditioning. Here we are creating high voltage and currents that we can send, high power voltages and currents that we can send to the real device. And if you go here, you can see one of my favorite tests. And this is something that my students do at the lab. My students in Norway, they used to go to the lab. Inside the real-time simulator, we have a network. In that network, you can simulate any kind of event. It can be a short circuit, it can be an open circuit, different kind of events. And the real-time simulator is producing the signals, and those signals are sent to the protection devices. Some signals coming from the relay, from the protection device, the ID, they can be read by the Universal Hill Connect, or some other information can be sent by Ethernet connectivity, okay? And here is the physical implementation. You can see the three different devices. We have at the top the relay, the Schweizer Cell 751. Here we have the real-time simulator, and at the bottom we have the Universal Connect. And what is interesting here for all of you is you can see the real wiring. We are connecting the relay with the Universal Connect. And from the real-time simulator to the Hill Connect, we use low voltage signals, okay? What I'm telling you is that from here, we are sending signal plus 24 volts. And here we are sending the signals to the relay, 230 volts and plus minus 5 amps, okay? Well, the students go to the lab. When they arrive to the lab, they have the electrical system. You can see here the electrical system. They can trip a signal for a short circuit. And when they are running the experiments, they can define the type of short circuit. This could be 3-phase, 2-phase, single-phase, whatever. And they can apply the short circuit. When they apply the short circuit, of course, the digital real-time simulator create these signals in real time. These signals are created in real time. And of course, you can see the overcurrent. And the overcurrent is applied to the relay in real time. Of course, you can see the feedback coming from the relay that the trip of the circuit and the breaker is open, okay? Well, here I am running right now of time, but there are some other examples here, but I will go to one that is relevant for the person that asked me about communication protocols, okay? Um, the reality is that power system has been populated with communication mechanism. For many years, we create several communication protocols and data protocols. One of them is the IC 61850. And the 61850 is a standard for the architecture and communication of digital substation. Inside that protocol, we can have several layers of data flows, data stream. We can go from the very slow MMS until the very fast sample values. And somebody asked me, how do we simulate the data network? In reality, with real time, we are not simulating. We are not simulating. We are generating the data streams. I mean, here we test a relay, ABB REDS 640. And in this relay, we can send signals using the IC 6850, and these signals follow this protocol. In real life, these signals must come from the digital CT or the digital VT, voltage transformer, current transformer, or emerging unit. But here in this cyber physical testing framework, we are using the real-time simulator to create the real data stream. For that reason, here we are not simulating, we are creating the real data stream. I mean, if you use any software like Whiteshark, a sniffer, you will see the data stream moving inside the local area network. You can see the data stream of IC 61850 going into the relay. And that is very powerful, because if you are interested on testing, for instance, cybersecurity, that is something that you can use, for instance, another digital real-time simulator, and you can create your data stream with the attacks and go inside the local area network and test the cybersecurity. I can see also another question in the chat that people are asking me if we can create or sell relay. Well, to be honest, there is a possibility that is what I call a virtual relay. Something that we have done before, done before is, instead of using the real relay, we create a digital twin. And the digital twin is very interesting because the digital twin is a relay that is simulated, but the relay is taking real signal, real voltages and real currents. That is what we call the soft relay. The soft relay is a digital replica, a digital reproduction of the original relay that can behave like the typical relay. But what is important is, if you can create a relay inside the real-time simulator, you can modify the algorithm and you can use for developing your own relay. I mean, if you want to test a different algorithm for the overcurrent or the distance, or if you want to create a physical location of faults algorithm, you can do that, okay? Here I want to close this discussion about the IC 6150, because you can create the real data streams, and with the real data streams, you can test the real devices. And this is a very simple and very realistic way to test the relays, but also this tool creating these communication protocols inside the real-time simulator and creating data streams, that opened the door. If you're interested in protection, that opened the door for developing virtual protection functionalities. And that is something that one of my PhD students in Norway is working. He is working on digitalization and virtualization of protection functionalities. And the core of this is basically communication protocols and real-time simulation, okay? Well, it's time to close this presentation. I am almost 1 hour here, and I would like to close this presentation telling you the following. To be honest, the electrical power system, they is still the same. We have the same generators, we have the same transmission lines. However, the new technologies, renewables, electric cars, batteries, and the integration of networking and computation is changing the way that the power system is behaving. And to be honest, to reduce the cost of analyzing these kind of situations, we need new tools. That is the reason that in the recent time we have been talking about cyber physical system, because the reality is that the same cables are still over there, the same generators are still over there, but the novel low carbon technologies, they came with networking and computational power that we need to include inside the power system analysis. And for that reason, it's the way that we are analyzing the system must change. And that is the reason that several companies, several utilities around the world, they are changing the way to do the simulations. Just for a simple sake, there are countries like Australia that they are considering and using real-time simulation for the studies in order to be sure that the system is able to be secure and resilient in low synchronous generation levels, okay? Finally, I have 1 more minute. I would like to tell you there is something that I highly suggest. If you are interested to have a flavor about real-time simulation, my friends and colleagues from Typhoon Hill, they have a product that is quite interesting. They call that Virtual Hill, Virtual Hardware in the Loop. Virtual hardware in the loop is basically a virtual machine that you can install in your personal computer, and you can run the same framework, and learn about real-time simulations. What is the advantages of the Virtual Hill? Well, one of the advantages of the Virtual Hill is that it's totally free. It's totally free, and as a consequence, you can download from the Typhoon Hill website. But also another important thing is that this company, Typhoon Hill, those friends from Typhoon Hill, they create a website that they have many documentation that allow you to learn about digital real-time simulation. Well, this is all for today, and it's time that I finish my presentation. Thank you so much, and it's time for question and answer.